Hello everyone. So this is going to be the third weekly live session on the NPTEL course on river engineering. So as you all know, it's a joint initiative of NPTEL and the Swayam scheme. And this course is being tutored by Professor Subhashish Datta from the Department of Civil Engineering at IIT Guwahati. And I am Abhishek Chakraborty, a PhD student under the Prime Minister's Research Fellowship Scheme at the Interdisciplinary Center for Water Research at IISc Bangalore. Yeah, so I have been uploading all the previous live weekly session on this YouTube channel. So please do check it. I will make sure to upload the videos, video recordings right after the class ends, and all the other slides and materials would be uploaded in this Google Drive folder. The URL for both the YouTube channel as well as the Google Drive folder are given here, and I will make sure to upload it immediately after the class. Lest there is some internet intervention. Yeah. So today I will start right away with the questions. We received a few of them in a discussion forum of the NPTEL course also. So I will be discussing all the numerical questions which were posted there at the discussion forum of the course on river engineering. So the first question happens to be that I mean, what would happen if the continuity equation is not satisfied at a particular location? So as you all know, the continuity equation, the equation was represented like this: the time derivative of the density plus the divergence of the density and product of density and the velocity fields. That can be represented like this: del by del x of rho u by del y by rho v plus del by del z of rho w equal to 0. So this was the continuity equation, and this should ideally not be ever invalid in case the all the measurements for the inflow and the outflow have been accurately taken. However, there can be certain conditions when this continuity equation can also be invalidated. That would mostly be because of a presence of a source or a sink term in within the volume, control volume considered, which would either generate water or which would actually suck up water from the control volume. So that source or sink can be represented as S in the right hand side of the equation, which was not initially discussed in the previous class. I think someone is trying to enter. Yeah. So that S term happens to be source or sink, relevant to source or sink, and source would be when the S is positive, and sink would be when the term is negative. So this source or sink term would depict there is a generation of mass right inside the control volume considered for this continuity equation. So uh, this may be because we are not considering it correctly while calculating uh, all the uh, flow variables. So the reasons, possible reasons why the source or sink may not be considered, maybe because of number one, infiltration may not be considered well. So infiltration, you might be knowing from your soil mechanics or probably irrigation engineering classes that infiltration is the art of, the science of flow of water into the soil. So that may be neglected completely, and that is why we might be getting an invalid continuity equation expression. So that might be one case in which the continuity equation may be invalidated, or secondly when the lateral flow may be neglected. However, strictly speaking, these are not the exceptions to continuity equation. If you measure the sink and source also pretty accurately, then the continuity equation uh, will never be wrong. Another way to express the continuity equation can be like this: del rho by del t. The first term is taken as intact, is kept as intact, plus the divergence of the density and the velocity product, the velocity vector product. Okay, so this can also be another way to express the continuity equation, where S is again the source of the sink expression. So V is the flow velocity vector field, and V can be represented as U of I cap plus V of j cap plus W of k cap, where I, j and k cap are the unit vectors, the conventional ones. So this was the first question which was posted there. I will be discussing other ones also. Yeah. Someone also asked about describing the fall diameter. So, as in the class, as in the video lecture provided by Professor Datta, it was given that the fall diameter is the diameter of a sphere having a relative density of 2.65 and a same terminal fall velocity as that of a given sediment particle in quiescent and pure water at 4 degrees Celsius. So, in order to just represent it in a mathematical formulation, we would be supposing that a sphere of any particle is falling inside a liquid. So, this is a sphere. This might be falling downwards. So, what would happen? I mean, there would be several forces experienced by this sphere, right? So, first of all, the most important force experienced by this sphere would be the force of gravity, which is the mass times the gravity acceleration due to gravity. Then, initially, when we let a sphere drop inside a viscous fluid or viscous fluid column, then it will initially accelerate. However, when the downward force of gravity happens to be balanced by the upward forces of the upthrust or the buoyancy as well as the viscous resistance. So, at that stage, when the forces are net forces are balanced, the sphere tends to attain a constant velocity, and that constant velocity is known as the terminal velocity. So the downward force of gravity would be balanced by two upward forces. The first upward force happens to be the viscous force, represented here by Fv, and the other one happens to be the buoyant force, represented here by Fb. So let us just take this condition of a sphere falling through a viscous medium. So this is a sphere falling through a viscous medium having let us say density rho l. So what may be the forces acting on the sphere? So there will be several forces. Number one is the Fv, the viscous force, which will act upward. Why upward? Because it's a resistive force, and since the sphere is falling downward, that is why the viscous force would be upward. The second important force happens to be the upthrust or buoyant force, which will again act upward as per the Archimedes principle. And the third one is the very fundamental force of gravity, that is the weight of the sphere. It acts downward and it is mass times the acceleration due to gravity, where m is the mass of the sphere. So let us just derive an expression for the terminal velocity. So at equilibrium we'll see that the net forces will be zero, and if the net forces are zero, then according to the Newton's second law, Newton's law, either the body is at rest or it is moving at a constant velocity. Because in case the net force was not equal to zero, then it would have some acceleration, and in this case there is a constant velocity, and that constant velocity is known as the terminal velocity. So it's very simple. Just uh, equate the net upward forces with the net downward forces. So the net upward forces happen to be the summation of the viscous force with the buoyant force, and the net downward force happens to be that of the gravity. Now the upward viscous force from Stokes law would be nothing but 6 pi eta r v, where v is the terminal velocity. V is the terminal velocity. And this expression from Stokes law comes from our very basics of class 11. Okay, so this was the Stokes law expression, where r is the radius of the sphere. R is radius of sphere, whatever the radius may be. Eta is the coefficient of viscosity, or in our technical terms, the dynamic coefficient of viscosity. And v is equal to vt is equal to terminal velocity. So 6 pi eta rv plus fb. Fb can be represented as, according to Archimedes principle, it would be the weight exerted by the mass of the liquid which is displacing the sphere. So let us just express it like that. So the buoyant force would be mass of liquid displaced by sphere into the acceleration due to gravity, just to make it into a force from mass. And mg is, this is nothing but mass of sphere times the acceleration due to gravity. So that is what we have found so far. I will take another slide. Yeah. So we know that the mass of the liquid can be represented in terms of the density. So the density of the liquid can be represented as the mass of the liquid times the volume displaced. The volume displaced by the liquid will be nothing but the volume of the sphere. So it would be mass by the volume of the sphere, that is 4 by 3 pi r cube. Similarly, the density of the sphere, this term we need for the weight of the sphere expression, would be mass of the sphere by 4 by 3 pi r cube again. So we just put it into the expression which we just got into equation star. So we will get the viscous force term, that is 6 pi eta r vt. Vt is the terminal velocity term. Then we're just converting the mass into mass using density. So mass is nothing but density times volume. This is the buoyant term, is equal to the mass of the sphere. So that is weight of the sphere. So that is the mass of the sphere times the acceleration due to gravity. So this is nothing but the downward acting gravity force. This is the upward acting buoyant force, and this is the upward acting viscous force. So if you try to solve the expression for Vt, you will get this expression: 2 by 9 r square g rho minus rho L by eta. So r is the radius of the sphere, g is the acceleration due to gravity, rho is the density of the sphere, rho L is the density of the fluid medium, eta is the dynamic coefficient of viscosity. Now we just look at this expression, rho minus rho L. So when we divide and multiply both the sides by rho L, yeah, first of all, in our case, in river engineering, the density of the liquid happens to be the density of the of water. So this is nothing but rho minus rho W. Now multiply and divide both sides by the density of water. So we get rho by rho W minus 1 times rho W, and rho by rho W is nothing but the specific gravity, minus 1 times rho W. So when you put the specific gravity term as 2.65 as was given in the definition, and you put the other quantities with respect to like eta and the and the density of water with respect to 4 degrees Celsius, then whatever r you get will be the fall radius. Corresponding to that, we will get the fall radius, and you just convert the radius into diameter by this expression. 2 times radius is diameter, so you will get the fall diameter. So that was the uh, numerical formulation of the same statement above. So what happens is that sometimes it is easier to find out all the other expressions apart from r. I mean, easier to calculate, and that is how we calculate the fluid. I mean, the sediment diameter indirectly. So we are done with the second question, which was asked in the discussion forum. Let's move to the third question, which was again asked. Yeah, but before going to the third question, which was asked in the discussion forum, I will like to derive the general condition for critical flow. So it is basically dependent on the something known as the specific energy, and I discussed it also in the video lecture for assignment 0, which is available in the YouTube channel. So specific energy, you all know, is nothing but the total energy at a given section with respect to the channel bed as the datum. So let us suppose this is the open channel. This is the total energy line. This is the flow depth y, and let us suppose this is the velocity head, that is alpha v square by 2g. So the specific energy is nothing but uh, the total energy head, just by subtracting just by taking the channel bed as a datum. So it would be y plus alpha v square by 2g, and alpha here is the kinetic energy correction factor, because v is the average velocity. So that is the thing. However, we know that the flow is mostly turbulent in open channel flows, and for turbulent flows alpha is almost equal to 1, or alpha is nearly equal to 1. So this implies we can straight away write the specific energy as the summation of these two quantities. So with respect to E and Y, there is a very famously known curve known as the specific energy curve. When we try to plot E versus Y with the flow depth on the Y axis and the specific energy on the X axis, it looks somewhat like this. This is, let us suppose, for discharge Q1. This is for discharge Q2, and Q2 would be greater than Q1. This is the E equal to Y line, dashed line. So this is how the specific energy curve would usually look like. Before moving further into the derivations, I will just make you recall the expression for uh, Froude's number. It's nothing but V, the flow velocity, times A by T. That is the A is the cross section area and T is the top width of the channel. Or you can write it is equal to Fr is equal to V by square root of GD, where D is A by T. We'll take another slide to explain it. Yeah. So now let us just come back to the question. The question was actually deriving the general condition for critical flow. Let us again make the specific energy curve. with y on the, I mean the flow of the flow depth on the y axis and the specific energy on the x axis. So we see that there is a minima to the specific energy. That minima is known as the critical specific energy, and the corresponding depth is known as the critical depth. Now there may be two cases when any depth of flow of water, depth of water is greater than yc, then velocity is lesser than the critical velocity. I will be describing it in later phase. So this would be a case of subcritical flow. That is, the Froude's number is less than 1. I will be describing it in a bit. And there may be another case when the y is less than yc. So this would mean v is greater than vc. So this would mean that it is a supercritical flow. So let us just come back to the specific energy expression, which is E equal to y plus v square by 2g equal to y plus v can be represented, sorry, v can be represented as the discharge by area, the cross section area. So it would be q square by 2g a square. So E is equal to y plus q square by 2g a square. Now at critical depth, specific energy is minimum. So what would we get? We would, in order to derive the expressions, we need to get a minima. So the first derivative should be 0. So let us take the derivative of that expression. So d by dy would become, someone is trying to enter. Okay, no. So d by dy would become, of this expression would become 1 minus q square by 2g are constant, and a square can be represented as, the derivative of 1 by a square can be represented as minus 2 a to the power minus 3 dA by dy equal to 0. Now let us suppose we take any cross section of the open channel. This is that free surface. So let us suppose we are taking a strip, and the strip thickness happens to be dy, and t is the top width of the open channel. Then we would know that dA, the strip cross section, is equal to the top width times the strip thickness. So this expression needs to be considered for the upcoming values. So dA by dy equal to the top width of the open channel. So we just need to put that expression in this above equation. So we would get something like this: q square t by g a cube equal to 1. So this is a very important expression, by the way, and this is the general condition for minimum specific energy. So let us just recall again the expression for Froude's number. The Froude's number is nothing but the flow velocity times g times a by t, where a is the cross section and t is the top width. So from the generalized expression which I just derived, q square t by g a cube equal to 1. From this expression, uh, something like this can be found out. So q square t by g a cube equal to 1. This implies, so q can be written in terms of A and V, that is Q is equal to A times V. So that would give V square G A by T is equal to 1, since Q square by A square is equal to V square. So this is nothing but the Froude number square is equal to 1. So this implies the Froude number is 1 at the critical, I mean, uh, so this would mean that the critical flow corresponds to the minimum specific energy, and at this condition the Froude flow, Froude number of the flow is unity. So Froude number is 1 at critical flow condition, and it corresponds to minimum specific energy. So just recall that I've actually derived the expression for a very generalized term, generalized open channel type. It's not only for a rectangular cross section. It's not only for a triangular cross section or a trapezoidal cross section. It's a very generalized expression. Now, just moving into the usage of this expression, for an example of it, we will be trying question number 4, and question number 4 is about comparing the critical specific energy of a rectangular versus a triangular cross section of open channel. So let us suppose we first consider a rectangular cross section. Someone posted a question about trapezoidal cross section also, and asked about uh, the critical depth for a trapezoidal cross section too. So I will be discussing it in the next question. But before that, I would like to discuss about the rectangular and the triangular cross section of open channels. And why have I kept the trapezoidal cross section later is because the triangular cross section and the trapezoidal cross section are a bit similar. So I will explain it. So let us suppose this is a trapezoidal cross section. The flow depth is y. The top width of it is t, which is nothing but the width of the rectangular cross section. So the area of the cross section can be written as b times y, which is very straightforward, and the top width is the width b. So E, the specific energy, happens to be y plus q square by 2g a square, and a square can be written as b times y. A can be written as b times y, so a square will become b square y square. So now let us suppose we take this expression Q. Q is equal to capital Q by V, which is discharge per unit width. So using this expression, E can be written as Y plus Q by V. Q square by V square can be written as small q square by 2g y square. Now in order to find the critical specific energy, we know that it is for a minima of the specific energy. So that can be written as d by dy equal to 1 minus q square by g y cube. We are just differentiating this term and equate it to 0 because it's a minima. So from it we get small q square by g is equal to yc cube. So we get yc as cube root of q square by g. This is a very important expression by the way. So again we can also write yc cube is equal to q square by g. I will take just another slide. So let us suppose we want to find E in terms of Y. So what might be the relation between the specific energy and the depth of the flow for rectangular channel? So for the minimum specific energy, it will be corresponding to the specific, critical depth of flow, that is for rectangular channel would be looking like this: 2g yc square. We are doing nothing, we are just replacing y with yc for it. So E min can be represented as yc plus yc cube. Why yc cube? It comes from this expression: yc cube is equal to q square by g. So q square can be represented as yc cube times g. So it is yc cube by 2 yc square because the g gets cancelled. So this implies that the minimum energy or the critical specific energy happens to be 1.5 times yc. So this is a very generalized expression for rectangular cross section. Now let us just move to a triangular cross section. The second part of the question asked us to do the same for a triangular cross section. A triangular cross section looks a bit like this. Let us suppose the depth of the flow is again y, and let us suppose the side slopes happen to be 1 vertical is to m horizontal, which can be printed as this also: 1 vertical is to m horizontal. So in order to find the top width, it's very easy. So this is y, so this will be nothing but m times y, and the other half of the top width will again be m times y, thanks to symmetry, because that is also 1 times 1 is to m. So the area of the triangular cross section can be represented as half into uh, into the base times the height. Okay, so half into the base. I don't know why I'm not able to write on the pad. Okay, let me use another slide for it. Okay, so the I'm unable to write. Yeah, A can be represented as half times the depth times the top width. Top width happens to be 2 times my. Somehow this is not working. Okay, so this is my square, and the top width is 2 my. Yeah, my plus my is 2 my. So I mean, forgive me because somehow my Apple Pencil is not working. I mean, I don't know why. Okay, so let us just go back to the specific energy expression: q square t by g ac cube equal to 1. So this will mean that q square by g is equal to ac cube by tc. This implies q square by g equal to ac cube by tc, and ac cube happens to be the cube of my square, so it would be m cube yc6 whole 6 by 2 myc. So this comes out to be m square yc5 by 2. So by now we know the term expression for yc. If we simplify it further, we will get yc as 2q square by g m square. M is the side slope, power 1 by 5. So this is the critical depth for a triangular cross section of open channel. So they are very different. I mean, the critical depth for a rectangular cross section versus that of a triangular cross section, they are very different. Now let us suppose we want to find the critical specific energy. So what is that? You just put y. I mean, replace y with yc, and you will get that expression. So ec is equal to yc plus vc square by 2g equal to yc plus q square by 2g AC square. So EC is, keep the YC term as same and just replace it. So we will get gm square YC 5 by 2g times 2 into m square times yc power 4. We are just putting the values of AC and Q into it. So finally EC will come out to be yc plus yc by 4. So this implies that EC is 1.25 times of yc for a triangular cross section. So that's the difference. For a rectangular cross section, it was 1.5 times of the critical depth, whereas for a triangular cross section, it is 1.25 times of the critical depth. Now we come back to the question which was originally posted in the discussion forum about the trapezoidal channel. However, I thought of solving it for a rectangular and a triangular channel also, just to give a brief idea about how the calculations are performed. So the question is, calculate the critical depth and corresponding specific energy for a discharge of 5 meter cube per second in the following channels. Number one is a rectangular channel where the width is 2 meter. Number two is a triangular channel where the side slope is denoted as m equal to 0.5, where v is to h is 1 by 1 is to m, just a convention which I used in the previous question. And number c is the trapezoidal channel where the width is 2 meter, m is 1.5, yeah, the side slope. So let us just firstly solve it for a rectangular channel. What happens for rectangular channel? So rectangular channel, we take first of all the discharge per unit width, that is the small q, is 5 meter cube per second in this question, divided by b is 2 meter, so that happens to be 2.5 meter square per second. So yc will be straight away found by the expression which we just derived, q square by g 1 by 3. So this we could also do using that generalized expression, by the way. The generalized expression of q square t by g a cube equal to 1. By taking that also we could do that. But since rectangular channels have a very easy to remember expression, so we would be doing it like this. 2.50 square by 9.81 power 1 by 3. It happens to be 0.86 meter for rectangular channel, and the critical the specific energy would be 1.5 times of the depth of the flow for a rectangular channel. So that is 1.5 times 0.86 meter, and it comes out to be 1.29 meter. So this is done. B is for a triangular channel. So we have just derived it in the previous question, so it would be very easy. Yc would come out to be 2q square by gm square, m is the side slope, power 1 by 5. So just put the numbers, 2 times 5 square by 9.81 times m is 0.5, power 1 by 5, and it comes out to be 1.83 meters. The specific energy corresponding to that would be, again my Apple Pencil is not working somehow, I don't know why. Let me take another slide. I'm very sorry for this, but it is not working currently. So we know Yc. What is the Yc? So critical specific energy can be found out from this expression of Ec is equal to 1.25 times Yc. So from it, EC will be coming out as 2.229 meters. But somehow I'm just unable to write it for some strange reasons. No, it's not working at all. Does anyone have any questions so far in the discussions which happened? Okay. Okay. So I will write it using my hand in that case. It's also not happening. I will check it firstly. Okay. Does anyone have any questions so far? I mean, in all the things which I discovered so far. No idea why it's not working. Is there any question so far? Please feel free to ask in that case. I wanted to discuss one more question actually, but somehow because of this malfunctioning, I'm unable to. I'm just unsure what to do right now. Am I audible first of all?
Yes, sir. So,
Yeah. So the pencil is not working. I mean, all of a sudden it deserted me. It betrayed me in between. I mean, I will just explain it orally. Then, in that case, what else can we do? So the trapezoidal channel happens to be, I mean, just similar to the triangular channel. You'll be also finding the area and the width of the trapezoidal channel, and uh, the area and the width would come out to be. I mean, that is what we will find firstly, and then we will go to this generalized expression of q square t by ga cube equal to 1, and from there we would be finding the the expressions for the critical depth as well as the corresponding specific energy of the discharge. So this is one question which I wanted to discuss. Then this question should be relatively easy for you guys. It is about calculating the alternate depths and the corresponding Froude numbers in uh, for a rectangular channel with a width of 2.50 meters and a specific energy of 1.50 meter when carrying a discharge of 6.48 meter cube per second. Before that, I mean, is there any doubt so far in the assignments? Someone posted that the assignment options are incorrect. I mean, so I also found some minor faults in the assignments. Like for assignment number 3, the question number 8 needs to have a minor correction. The Froude number is actually a dimensionless quantity, and in that assignment, all the options for Froude numbers are with the unit meter. So just omit the unit meter, but the numbers are correct. So find the Froude number first and just omit the unit meter in that. And again in question number 10 of assignment number 3, the alpha given in the question is that of the kinetic energy correction factor. So take that into consideration. Kinetic energy correction factor is nothing but the alpha. So you can do it very similarly by the first principles. Uh, you take the specific energy. Yeah, you take the specific energy and just take alpha equal to 1. So E will be y plus, I mean, alpha is whatever given in the question. So E equal to y plus alpha times v square by 2g. So that is how you will find the specific energy and then proceed to get the solutions. Uh, are you facing any problem in the assignments? Assignment number 3 apart from that, or assignment number 2 also? I think the deadline for assignment number 2 is over by now. Anyways,
First two are over, sir.
okay, yeah, first 2 are over, right?
Yeah. Now
So
the third one we have to complete it by this week, by 17th, I think.
So did you go through the questions?
Yeah, I have gone through it, but I didn't do it actually. I thought to do after this class actually.
No, no issues with that. I mean, I
Please
will be,
reshare that presentation, sir. Then I think it will
yeah,
go.
yeah, I will be sharing the presentation as well as I will be, I mean, the 2 questions which I could not cover because of this malfunctioning, I will be typing it, I mean, typing the equations here and then we'll share with you. So it will take some time, but I will make sure to send it to you by the end of midnight today. So that
Okay.
will also be done. Don't worry about that. I'm very sorry again. I mean, suddenly this pencil malfunctioned for some unknown reasons. But I think I have done some sort of what do we say? I mean, whatever important points I wanted to discuss, they have been discussed by me by now already. So this was, I mean, the derivations have been discussed. All the remaining questions were just number type. So I will be discussing it also. I mean, in case you don't understand it, I will again explain it in the next live session. By then, I will try to sort out this issue too. Uh, we will just look at the assignment questions also, just in case there is something missing. Just give me a moment, please. Let me check the assignment questions firstly. I will orally tell you. I mean, what actually is needed. I mean, in assignment three, in that case. Okay. So is it visible? Oh yeah, I think it should not be visible currently. Yeah.
No.
Your
No,
entire
sir.
screen. Yeah. Is it visible? You yeah. Is it visible now?
Yes, yes. Now it's
Yeah. Yeah.
visible.
Thanks. So there is one question which is very interesting and very different from the other questions in the assignment. That is question number 7. So this is pretty similar to the solved example which was discussed in one of the video lectures by Professor Datta, and this is kind of an application of the Saint Venant's equation. Okay, so seventh would be done using that. Then question number 6, uh, yeah, this is again finding the subcritical and the supercritical depths. So you just need to be very sharp with the specific energy expression, and you should be able to solve it. Then the expression on trapezoidal channel. Yeah, so this is something new. Yeah, again, there is a minor fault in this question. They have asked you also to estimate the Froude number of the flow in that reach, and the Froude number is actually a dimensionless entity. So meters, I mean, they have given it in terms of meters. You should just omit meters, but the numbers are correct. So whatever number you get, let us suppose you get 0.49, then tick this option A. If you get 0.35, then tick the option B. So that is how you should proceed with it. So this unit is incorrectly given. Then question number 9 is about a sluice gate, which is used to control the flow in a rectangle. Okay, so this is again nothing but the application of the same specific energy expression, E is equal to y plus v square by 2g. So using that, you should be able to solve question number 9 also. Then question number 10, a trapezoidal channel having a bottom width of 20 meter. Okay. So this is a trapezoidal channel. So this alpha is nothing but the kinetic energy correction factor. So E, the actual expression for specific energy, happens to be Y plus alpha times V square by 2G. And uh, alpha, I mean, which I already discussed somewhere. Yeah, it is supposed to be E plus alpha times V square by 2G. But since alpha is very near to 1, so we neglect that. But you don't have to neglect this in this question at least. So go ahead like that, and you will be able to find the critical depth of the trapezoidal channel. I wanted to discuss the derivation of the specific energy in the critical depth in this lecture, but because of this malfunctioning, I could not do it. But I will be typing it manually in the presentation, and will be sharing it with you. So no need to worry about that. Apart from that, mm, yeah, these are just sort of one liners, so you should be able to solve this question too. Yeah, and someone asked in the discussion panel about sediment collection also, right? uh, I think he asked about how the sediment is collected. Yeah. So he is asking about, can you give one lecture regarding how the sediment is collected from a water body? If you have pictures, it would be more clear. So people usually either take course during their, fluvial excursions, trips to collect the sediments, or that they collect a definite uh, volume of the floating water if they want to find out the suspended sediment quality or quantity, and that is how they proceed with it. So this question I discussed, and apart from that, all the other questions which were posted, I have already discussed in this live session. Apart from that of the trapezoidal channel. So someone asked about satisfaction of continuity equation that was discussed in the very first slide of today's live session. Someone asked about the fall diameter. I discussed it using the balancing of the forces terms. Then someone asked about the trapezoidal term, most probably, and that I could not discuss, but I will be putting the values here. And someone had some doubt about the validity of the, whether the options of the assignments are correct or not. We checked that, and we found out that all the options have, among all the four options given, one of them is actually correct. And in case you are not getting the correct magnitude, then you should take the option which is nearest to it. So that's it, I believe, for from today's class. But I would just give a brief recap before bidding goodbye to all of you for today. Yeah. So we today first of all learned whether there can be any exceptions to the continuity equation. So we learned that, yeah, that can happen in case there is a source or a sink of water into the system, into the control volume considered. So that may happen because of generation of mass, or maybe destruction of mass because of some because of some sink sucking up water from the control volume. And we also discussed several reasons why this may be happening. In most of the subsurface flow problems, it may be because the infiltration is not correctly considered, or the lateral flow may not be considered correctly. Again, I mean, I would just put some light on this expression of the continuity equation. This expression actually is very interesting. Why? Because in nature there are several other equations also which are pretty similar to this. The heat conservation equation is also pretty similar, just like the continuity equation for the fluid flow. So this is the peculiarity of these expressions. Similarly, in computer sciences, the information theory also has a very similar expression. So that is why this expression becomes so interesting and so salient. After this, we discussed the several forces acting on a falling sphere in a viscous liquid, and we observed that I mean, as the net forces happen to be zero, the velocity of the falling sediment particle will be something known as the terminal velocity. So we found it out by derivations, and uh, we found that it would be I mean, the fall diameter would be found out from this expression. Then we derived the general condition for critical flow. Uh, this condition is very important. If you ever get stuck in any problem related to critical specific energy, I mean specific energy or critical depth, just go back to the basics. This is the first principle: Q square T by G A cube is equal to 1. Always go back to the basic. Rather than, I mean, that is what I would advise. Rather than memorizing expressions, just go back to this expression. It would do you very good. I mean, you just need to remember one expression and everything else will be solved. Yeah, and we also found out that the Froude number is unity at critical flow condition and it corresponds to the minimum specific energy. Yeah. So one doubt may be that why are we not considering the second derivative? I mean, we all know that for minima, the the first derivative happens to be zero, but the second derivative should also be positive. Why didn't we check that? Any opinion? Any opinion on that? Why didn't we check d2 e by dy square also? Please feel free to share. I mean your opinions. Okay, the thing is that we didn't check that because I mean the thing is that if d by dy is equal to 0, I mean you will always get d2 e by dy square to be I mean positive in this case because I mean the slope changes only once, so that is nothing. I mean that is not a worry. I mean at least for such questions. Then, for the last question discussed today, we found out the critical specific energy for a rectangular versus a triangular cross section. We found out that the minimum specific energy for a rectangular cross section is basically 1.5 times the critical depth, and for a triangular cross section, it's basically 1.25 times the critical depth. And I could not discuss two other questions. I will be, I mean, typing it here and will be sending it to you by tonight. Please feel free to ask me any question. If there is any question, please feel free to ask me. Is there anything else you want to ask about the assignments or something? Okay, so I believe we are done for the day then. If there is no question, yeah, yeah. Please
Please,
ask.
please give the expression for trapezoidal channel, critical depth and critical force. That is,
Exactly. I tried the same, but my Apple Pencil actually stopped working. So by tonight, I will be. I mean, I have to upload the slides, Nagendra. So
okay, sir.
I will be typing the expression in
Yeah.
the slide and will be uploading it by midnight. So
Okay,
I'm
sir.
very
Thank
sorry
you.
for that. My Apple Pencil actually malfunctioned. It's not working anymore. Otherwise, my plan was to derive the same. I mean, you
Yeah,
posted
yeah.
that question, right?
Yes, sir.
It
Yes.
was a very essential problem because most of the open channels happen to be trapezoidal itself. So
Channel.
my
Yeah.
plan was to first derive the expression for triangular cross section and then move to the derivation for a trapezoidal cross section. But somehow I couldn't do it because of this malfunctioning. But I will be typing it and I will be I mean post uploading it by tonight. So I'm very sorry for that, but I will be doing it by tonight.
Okay, sir. Actually, in assignment also there is one question between subcritical and supercritical depths also. For
Yeah, which one? Which one? We were just
yeah, but
discussing the assignments.
yeah, assignment three, sir.
Just give me yeah. So which one are you talking about?
There is a question. So
Which
we
number? The
mentioned
number
between.
is.
Uh,
I think I have shared the screen also. You can check.
yes, yes,
Question number 8.
so question number eight. Anyhow, that is based on your trapezoidal channel
Yeah.
critical
So
depth reached only.
yeah, I think
Apart from
in case you missed out, the Froude
yes,
number is
yes,
a
sir, nine,
dimensionless quantity.
nine,
Okay.
sir, nine. Question number nine. So which is displaying sluice gate?
Yeah, yeah, yeah.
Yeah, this one.
Yeah, so it is a very easy expression. Just go back to
Yeah,
your first principles. Basically,
yeah,
the specific energy will be represented in terms of y plus the v square by 2g. Just use as
yes,
expression for section 1 1 and the section 2 2. You will get the answer.
yes.
Okay,
And there is
and
a
and
one.
and for
Yeah,
question number 8, the Froude number is actually a dimensionless quantity. The meter here should be omitted. It's I think someone has I mean wrongly written meters for Froude number.
yes,
Froude
yes.
number is dimensionless. Okay, Nagendra.
Yes, sir. Sir, actually, there is one doubt that is general. So that is subcritical depth will be the lower part of the specific energy curve, or that will be upper part of the specific energy curve. So that you
In
please
general, in general, subcritical depth is the upper part. I mean, the y is more for subcritical
more
depth.
than YC, right? Yeah.
Why? Because E is equal to y plus v squared by 2g. So if y is more, then the v is should be less for
Yes.
subcritical depth.
Okay.
Okay, okay. So v is less, then the Froude number will be less.
Yeah. Yeah.
So I'm saying in general, there may be
Okay.
exceptions, but usually for subcritical flow, the depth is more than that of a
Okay.
supercritical flow.
So that will be upper part of the specific energy curve.
Exactly,
Subcritical.
exactly. In general, there may
In
be
general, in
exceptions.
general. Yeah, yeah.
There may be
Okay.
exceptions.
Yeah. Okay. Okay.
Anything else?
That is on. Thank you, sir.
Okay, okay. So I will be typing it and I will be uploading this. I mean, live session presentation by tonight. Okay. So your trapezoidal section doubt will also be sorted out. Okay, Nagendra.
Okay, sir. Thank you very much.
Okay, okay. So thanks for coming. I will be uploading it by midnight. Thanks. Thanks again.